We're going to come practice a couple examples looking at limiting reactant and access reactant. Again, these are important examples because we want to make sure we're developing or designing the experiment appropriately. We don't want to waste a bunch of chemicals we don't need to waste by making a huge amount of access. We also want to make sure the reaction actually goes to completion. So in this example, we have 98.0 grams of B2O3, which we're given a molar mass of 69.62 grams per mole, and 125 grams of HF with a molar mass of 20.01 grams per mole. These are combined and allowed to react according to the given equation. I definitely took away your equation. I will give that back. What mass of the access reactant will be left over? Okay, so my given equation here, I apologize, I deleted a bunch of equations and I forgot to leave this one in here. B2O3 reacts with 6 moles of HF to produce 2 moles of BF3 and 3 moles of water. And again, like discussed previously, you don't have to do this next step, but I recommend it because it helps you guys identify that it is in fact a limiting reactant problem. So write down underneath the reaction what you're given. You're told 98.0 grams of B2O3 and 125 grams of HF. Just seeing that there, seeing something listed under both reactants, immediately tells me that this is a limiting reactant example because I have amounts for both reactants. Not only that, it does say, what mass of the excess reactant will be left over. Yeah, I need to know that as well. But just seeing this immediately tells me. Now, if you're unsure what to do, follow the 6-step method. It will get you to the right point. I like making things easier on my life, so I like converting from one to the other. So I'm just going to pick one, and I'm going to say, well, how many grams of HF do I need to react all of my V2O3? I don't know what my limiting reaction is yet, and I got to figure that out. So 98.0 grams of B2O3, convert that to moles. 1 mole of B2O3 is 69.62 grams. Now you're in moles. Now you can convert to moles of HF. I see from the balanced reaction that 6 moles of HF react with 1 mole of B2O3. I know that HF weighs 20.01 grams. I could add it up if I had to, but it did give it to me, which was nice and convenient. And I get an answer here of 169 grams of HF. So what this means is I need 169 grams of HF to react all 98 grams of my B2O3. I don't have enough. Because I don't have enough, I know that this is my limiting reactant and this is my access reactant. I don't have enough HF, so HF is my limiting reactant. So what I'm going to do now is then I'm going to figure out, okay, if I know HF is my limiting reactant, then how much B2O3 do I need to react all of my HF? I'm going to basically do the calculation I just did, but I'm going to do it the opposite direction. I'm going to say, okay, well then how many grams of B2O3 are needed to react all of my HF? I have 125 grams of HF, 1 mole of HF weighs 20.01 grams. The balanced equation tells me that 1 mole of B2O3 reacts with 6 moles of HF, and my molar mass of B2O3 is 69.62. For every 1 mole of B2O3. This is 72.5 grams of B2O3. So what does that mean? That means that 72.5 grams of the B2O3 is needed to react all 125 grams of my HF. I have 98 grams. So 98.0 grams of B2O3 available minus the 72.5 grams of B2O3 that are going to react leaves me with 25.5 grams of B2O3 in excess. Again, limiting and access reactant problems, they could ask you what the limiting reactant is identity-wise, what the excess reactant is identity-wise. How much, once you find the limiting reactant, how much product can you make? How much access remains, like this question asked here. We could pull percent yield into this. There's a lot of things we can do with these questions. What about this example? How much nitrogen gas is formed when 18.1 grams of ammonia and 90.4 grams of copper 2 oxide are reacted? It then gives me the information to write out the question or the balanced equation. It says ammonia, which I know from above is NH3. So ammonia, NH3, in ammonia is a gas unless otherwise specified, okay, is going to react with copper 2 oxide. I apologize. I will make sure that the words are in here. I meant to put the words back in here and I definitely took them out. So ammonia is going to react with copper 2 oxide. So I know that copper 2 means Cu2 plus, oxide means O2 minus. So it must be a 1-to-1 ratio. CuO, that will be a solid. And this is going to form nitrogen gas. Nitrogen is one of my diatomics. Solid copper metal, and water vapor. Now I need to balance this equation. So I've got 2 nitrogens on the product side, so let's put 2 nitrogens on the reactant side. That gives me 6 hydrogens on the reactant side, so let's go ahead and get 6 hydrogens on the product side. That gives me 3 oxygens on the product side, so let's give me 3 oxygens on the reactant side. And that gives me 3 copper on the reactant side, so let's go ahead and give me 3 copper on the product side. So I've got 2 moles of ammonia reacting with 3 moles of CuO, producing 1 mole of N2, 3 moles of copper metal, and 3 moles of water. 2 nitrogens, 6 hydrogens, 3 coppers, and 3 oxygens. It is in fact balanced, and we are good to go. Now what I want to do is write down underneath the equation what I'm told. I'm told I have 18.1 grams of NH3 and 90.4 grams of CuO. I want to know how much nitrogen gas is going to be formed. I don't know what my limiting reactant is yet. I have no idea what my limiting reactant is. So I'm just going to pick one. I'm going to say how many grams of NH3 are needed to react all of my CuO. Again, I just pick one. So I've got 90.4 grams of CuO, 1 mole of copper 2 oxide, weighs 79.55 grams. And I see from my balanced reaction, 2 moles of ammonia are consumed for every 3 moles of copper 2 oxide consumed. This cancels my grams of copper 2 oxide. My moles of copper 2 oxide, I'm in moles of ammonia now, but I don't want moles, I want grams. So the molar mass of ammonia is 17.03 grams for every 1 mole of NH3. That cancels out my moles and gives me grams, and I calculated this out to 12.9 grams of ammonia. Again, what does that mean? It means I need that much. This is needed. I check how much I have, and I have enough, which means that my copper 2 oxide is my limiting reactant, and my ammonia is my excess reactant. So we do have enough. We have enough ammonia to react all of my copper 2 oxide, so copper 2 oxide is my limiting reactant. That also means that the copper 2 oxide is what's going to control how many grams of nitrogen gas can be formed. So 90.4 grams copper 2 oxide, 1 mole of copper 2 oxide is 79.55 grams. I look at my balanced reaction and I see that 1 mole of ammonia, 1 mole of nitrogen gas is being produced for every 3 moles of copper 2 oxide consumed. And now into moles of nitrogen. I'm going to go ahead and add up the molar mass. It is N2, remember that. So it is 2 nitrogens added together. So a mass of 28.02 for every 1 mole of N2. So again, 28.02 grams of N2 for every 1 mole of N2. Calculate this out, and it's going to give me an answer of 10.6 grams of N2. So with this reaction condition, I can produce 10.6 grams of nitrogen.